All right, I'm going to walk through an example in here that relates to multicollinearity and variable selection. This is related to a homework set, and so I've got different pieces down here noted. Anyway, so I'm going to read in the data set. Actually, I've already done that, but I'm just going to look at what variables are there. So again, this is a data set just for the purpose of making this video. It doesn't actually have anything to do with any homework set or anything like that. So I've got Y and X1 through X6, and I can get the 5-number summary out for them as well. Just run that, and I can just take a peek at them if I want. So the questions are related to this. The first thing to do is to run a regression. So I'm going to get a regression out. I'm going to call it M. I'm going to say LM equals, I want to regress Y on all of the X variables. In this case, since that's all that are there, the Y and the X, I'm just going to use the dot, and I'm just going to say data equals H07, which is what I called the data set. So I'm going to go ahead and run that and not do anything else for the moment. But when I look at this, one of the questions is, if we're looking at the homework set, what about the relationships in here? So for this, I want to build multiple scatter plots all in one go. So I'm just going to say pairs for H07 in there, and to see what that does for me. And it produces this set of plots over here. You can see on the right. And from there, I might look at and ask, well, which of these suggest a positive relationship? Do any suggest a negative relationship? Or with some of them, is it hard to tell? So what I see here is it looks like X1 and X4, because I'm looking at this here. This is the relationship between X1 and X4. Looks like it is quite positive. There's a strong relationship. Other relationships are harder to see in this set of graphs with these bivariate relationships, but this is one example where it appears to be a strong positive relationship or correlation between those two variables. Other than that, they look kind of hard to tell. All right, so then part of the homework question here that we might be looking at, we're curious about how to find an influential observation, or we want to look at QuickSD. So I'm just going to put in here par MF row equals this. So I just want to get all of the plots on one page together, or in one pane. And then I'm going to just choose plot and the model M. Right. So run these through, excuse me. And I get this plot over here. Now, when I'm looking for an influential observation, I'm looking for something down in this part of the graph, or in this particular graph. And I'm looking for something that maybe has a large Cook's distance. In this example, none of them have a large Cook's distance, but it could have something here where it might show a curve and say 1, let's just suppose, and then there would be something out beyond that, and that would be an influential observation, or which are the Cook's distance there, and it would likely label that observation. So for example, in this case, this one is observation 12, and it's shown there. So it would have something like that. In this case, there aren't any influential observations. There isn't anything with a large Cook's distance when I look at that picture. All right, then it says remove the influential observation if you find one, and find the mean. So let's just take a look at a couple of things here. There are different versions of the homework depending on which data set you get. So let's just suppose we want to remove an observation. Let's create a new data set here, H07B. And we might take H07, and we're going to get a subset of this. Let's just say we want to remove observation 12. So we type -12 in there, and then do that. And that took observation 12 out. And we can now check what the mean is. So we could say mean y, or let's say H07B y, and run that. And it gives us a number. And then we can just compare that. If we just use the H07, and it looks like they're different numbers. We could do a little bit more detail in there to check, but yeah, we've gotten rid of observation 12 in there. Another thing to check on that, though, might be to say something like nrow H07, and it says they're 197, and then nrow H07B, whoops, and 196, right? So looking down here, now that doesn't tell us which observation it dropped. So we're just relying on that it did the wrong thing and it dropped the observation 12, but that's what's going on there. Then it also says, look at individual coefficient p-values and p-value for the f-test. Well, for this, I need the summary of the model. So again, a different version of the homework question that people might see. It says, look at the p-values. So when I'm looking at the p-values for the individual coefficients, I'm looking over here. Nothing is highly statistically significant. This one is the lowest p-value for x2, but again, it's not even statistically significant at the 0.1 level. And then for the f statistic, this p-value is quite large. So again, it doesn't look like anything is statistically significant in this particular model. And even with this f statistic, it suggests jointly that they might all be zero, right? That these variables don't help to explain much in the model. And you can see a very low R-square there too. So now, it's moving on. It says find the smallest p-value. So we already saw that here. Smallest p-value is the 0.12. So hopefully that's clear there. Look at the residual plots. Do the errors appear heteroscedastic? So I'm just looking at this plot, and it doesn't appear to be the case. At least it's not. There's not a strong case for it, right? I'm kind of looking here. Yeah, if I want to capture this low spot in there or this high spot in here, but broadly, I don't see what I would call compelling evidence here. So I'm going to expect a fairly large p-value if I do an actual test for this. But here I'm looking, if I see things that were to fan out more, so if I saw something more like that, where the dots were spreading out more or funneling down, that would be more of an indication of heteroscedasticity. So that's what I'm looking at. No, they don't appear heteroscedastic in this case. So then the next thing is, it says conduct a Bruch-Pagan test. So with that, you want to make sure that you have the LM test installed. I already do, but we'll just get that there. And then I can do BP test. And what am I doing it on? M. So just go through this here, BP test. And it actually gives a p-value. A little surprised there that it's so low. Maybe it's not 0.005, but it does give me an indication that yes, the errors are heteroscedastic. So for me, that's a little bit surprising, right? As I just noted, I'm looking at this, and it doesn't appear to be that strong. But if I want to reconcile that with this here, which again, I would fail to reject at the 0.05 level, which is the conventional level, is the standard and typical, but I would reject at the 0.1 level. So so it just depends on how you want to interpret that precisely. But if I now want to reconcile this, right, it's a fairly low p-value. Again, doesn't meet a 0.05 cutoff. So I would still, at the 0.05 level, reject the hypothesis, fail to reject the hypothesis that the errors are homoscedastic. But how might I reconcile this? Well, I might look at this kind of a cutoff in there, or maybe a different cutoff over here somewhere, but these tend to fit mostly in this box here. They look fairly, maybe a lower range. And then if I look at the ones beyond that point, they look to be a little more spread out. But again, not super clear. We would reject the homoscedasticity assumption at the 0.1 level, but not at the 0.05 level. So, all right. The next thing that I want to do here is find the VIFs. So that's going to also take well, I've got the package installed already, but I would want to have the car package installed, but it's already there, so don't worry about it. But I want now VIF, and I'm going to put the model in there. So it gives me these VIFs, and I get 70 here, 1.0, 70, and so on. Which is the largest? It's 70.18 down there. Does that suggest a problem? So my answer is yes, it is larger than 10. 10 is a fairly common rule of thumb or checkpoint for VIF being large, but it's not a universal guidepost. Some people might have a different preference, but 10 is fairly standard. Now we want to find the condition number. So the condition number involves a few different little pieces here that we're going to have to look at to get this, including we're going to need to find some eigenvalues. We need to find some things here, but let's go ahead and find our, I'm going to call it CM for correlation matrix. And so this I'm going to put in as matrix, since I just need that part in there. And then I'm going to do COR for correlation. And what do I have in here for correlation? I've got the H07 data set, but I don't want, so I'm going to use all the rows, so comma to get all the rows, but I don't want the first value, the first column, sorry, not the first value. I don't want the first variable. So I'm going to put -1 there. And let's see, do I have the right, oh, I need close brackets. Looks okay. So let me see if I run this. And then I just want to see what I've got actually here. So I'm just going to say CM and run that. And I can see what it did, right? X1, it gives me these correlations. And I can see X1 is perfectly correlated with itself. And it's got a very high or strong correlation with X4, which isn't surprising given that X1 had a large VIF, X4 had a large VIF. So hopefully that's not too surprising. Okay, but now what we need are the eigenvalues if we want to get the condition number out of here. So I'm just going to call it the CN for condition number. And what I'm going to have here is, again, I need to get these eigenvalues, but I'm going to take the square root of the max of the eigenvalues. So eigen, sorry, for this correlation matrix. And I'm actually just want the values part. So I'm going to put this values in there too. And that's going to be the ratio of that over the min. So I'm just going to copy and paste this here. But I'm going to switch from max to min. and then see what this does for me. And then I want to actually see it. So let me get the number out. And it says 16. So is that large? Well, it's not larger than 30. 30 is again, a guidepost, a checkpoint for thinking that this is quite large and needs the issue of multicollinearity needs to be addressed. There are other checkpoints. 15 suggests it might be a problem. Again, these numbers aren't entirely arbitrary, but different researchers might have different cutoffs that they like. So in this case, it appears that there might be a problem. It appears moderate at least, right? It's over 15. It's not 30. 30 is a definite indicator of a problem. 16 suggests there might be, but combined with the large VIFs suggests that maybe something is going on here that we want to be aware of. So from there, let's say we want to go on and use this LEAPS package, and we're going to do some model selection items. So this is going to require, again, I think I already have it installed, but we want the LEAPS library. Oops. Yeah, so we'll just run that. I already got it in there, but so here what I'm going to do with this LEAPS library is I'm going to get a model for mallow CP. So I'm going to do M, and I'm just going to call it CP for mallow C, I guess. CP. Anyway, so then what I'm going to do is I need this LEAPS function. So I do LEAPS, and then what I need to have in here is I need an X matrix and a Y matrix. So what I'm going to do here is for the X, I'm going to say X equals, and I'll just say as dot matrix. And here I'm going to have my data set, H07, and I'm going to have all of the rows. And again, I'm going to remove the Y variable as before. You have some different options about how exactly you might want to type this in, but you could do that. And then for the Y, I'm going to use the Y variable. So then I'll just say I want method, and actually let me just say here I'm just going to say nBest equals 1. So give me the best model for each number of variables that might potentially be included, and then method I want in here to choose CP. So LC. With this, let me just point out again that as you're working through this, less familiar with LEAPS, you can come down here. I'm down at the bottom, and you can type in help. Oops. LEAPS, and hit enter. Oops, enter. And you can get some additional help with this again, right? Or go back to the lecture video and notes as an example there too. So we've got this. Let's just run it. It pops that out, but now I want to look at it. So let me just pop m.cp and see what it does. Okay, so now it's given me this output here, and it might be a little challenging to read, but what it says is that for the model with only one variable here, the best model has the second variable. So that would be, whoops, that would be x2. For a 2 variable model, so down here, it's going to have variable 2, which is true, and variable 5. So x2 and x5 would be the best 2 variable model, right? So that's what's going on there. Now I can come down here and look, well, what's the objective here with mallow C? The objective here is to have the lowest malloc. So I come down here and I look at these values, and it looks like choosing the one variable model might be the best. Now, there's another guidepost that you can use, which is that so you could choose this because you want the malloc to be lower than the number of variables in there. But anyway, but in this case, we would go with this. Right? So the one variable model, we choose a model with x2 only. The next part, though, says, well, let's instead of using malloc, let's use adjusted R-square. So get that down here. And I'm going to just change this from CP to be ADJ R2 for adjusted R-square. Again, if you're getting familiar with this, you can come over to the help window and see that there's that option there. But it's just there. And then let's change this to adjusted R-square, just for purposes of keeping things straight. So run this, and in this case, so what I want to do is I want to maximize adjusted R-square. So again, I can tell one variable model, it says choose x2, two variable model, it says choose x2 and x5. Right, so those would be the variables, and then so on. Right, so three variable model would be 2, 3, and 5. So which variable does this one choose, though, or which number of variables? Right, so it's the objective here is to maximize adjusted R-square. So 0.007, and then it goes up to 0.01. So the two variable model is better than the one variable model based on this. And then 0.0122, so that went down, right? So it went down from 0.01027 to 0.01022. So this version chooses the two variable model as opposed to the one. Right? So comparing them, they both chose x2 for the best variable, and then the best two variable model would be x2 and x5, but they disagreed in terms of which was actually better, if you will, right? So the malloc gave us the one variable model with only x2, the adjusted R-square gave us the two variable model x2 and x5. Right? So now just run the this optimal model, and we want then, so we'll call it model optimal, OP for optimal, and LM, we are going to have Y, and we're just going to have x2 plus x5, data equals H07, and then we can get down here a summary of our model optimal, and then we could also plot it too if we want. We won't do that, but so just go through here and get that out, and then run this summary, and we can look at what it's got going on for us here. So again, very small R-square. This increased the F statistic though, but you can just see what's going on here. So still x2, small, but not particularly small p-value. So it's not even statistically significant at the 0.1 level, although it's close. And x5 definitely not statistically significant there. But hopefully that just gives you some help in terms of walking through some of these things. Again, an additional example of using some of these lines of code and how to work for that. So hopefully that's helpful.